Log on, tune in, find out. Another good idea from Cambridge.
And Kostis, who's in the audience somewhere, there. And I should point out from the very beginning that Andreas Gustafsson also had very similar ideas and has papers on similar topics. Okay, so my motivation, briefly set the picture. Back in 2007, there were effective descriptions of M2-branes proposed. And as you probably know, this created a lot of interest. So these two models were the Berger-Lambert-Gustafsson model. And by now it has over 542 citations. The other model was the Aroni, Bergman, Jaferis, and Maldacena paper. So even more citations, right? So it was clearly one of these big waves. And if you know that there's an effective description of M2-branes, then the tempting question is, of course, to ask if there's a similar description for M5-branes. Of course, that there are various reasons why it shouldn't exist, but at least one can try, right? And so one possible way to approach the problem is just to look first at the BPS subsector of this model. This has a chance, at least I think, of existing. And this is a good way to approach the problem for two reasons. First of all, this was exactly the way in which the M2-brane models were found. So people first looked at a certain BPS equation which was proposed, used that equation to determine supersymmetry transformations, closed the supersymmetry algebra, and this way they found the equations of motion. So looking at the BPS subsector worked in this case, so let's try it here. And furthermore, the BPS subsector is interesting itself from my point of view because I come from twistor geometry and so on, from classical integrability, and it would be interesting to look at this BPS subsector from that perspective. And the results, just to summarize already what you can expect. First of all, integrability is also found here in this context, in the M5-brane BPS subsector. Then loop space turns out to be very helpful in this context. And then finally, I show that loop space also appears from various other perspectives very naturally. Okay, so let's come to the integrability and a quick overview actually of how the picture fits together. So first of all, there's what I call the string theory picture, which deals with a twistor description of magnetic monopoles. This one exists due to Hitchin. These are so-called Hitchin's mini twister spaces, which gives you a nice description of magnetic monopoles. And as in every twistor description, this description relates cohomological data on a twistor space, so vector bundles or whatever you like, with certain conditions to solutions on for the magnetic monopole equations. And this twistor description is underlying the ADHMN construction. So if you look at how the twistor description works, then you can switch to a picture which is based on so-called monads, and then you arrive at the ADHM construction for instantons or ADHMN construction for magnetic monopoles. But then now you observe that the ADHMN construction is just a very special kind of Fourier-Mukai transform or T-duality. So there's some hope to get a string theory picture out of that. And indeed, so you can rephrase everything that appears in this ADHMN construction in terms of D1, D3 branes, and this is work due to Diaconescu and Simpis at the end of the 90s. And the nice thing about this ADHMN construction is that it allows you to switch perspectives between the D1 and the D3 branes. So now let's look at the M-theory situation for this. I guess this one ran out of batteries. So first of all, the M-theory analog of magnetic monopoles are so-called self-dual strings. And there indeed exists a twistor description of self-dual strings, and we found that only last November. We were quite surprised. There's a new twistor space which hasn't been discussed in the literature as far as we know. But Martin talked about this last week already at DAMP, so I didn't want to bore you again if you had happened to be at this talk. And so it's reasonable to expect that there's a generalized ADHMN construction that connects both the effective description of M2 and M5 branes, well, the BPS sectors at least. Okay, this is really out of batteries now. Okay, so let me describe this a little bit in more detail and show you how this lifts to M-theory then. We start with the D1, D3 brane configuration, which is depicted here. So we have a big D3 brane, and we have a D1 brane or stack of D1 branes ending on it. And they're aligned as this, so they have temporal direction, which we ignore. We are only interested in static configurations. The 1, 2, 3 direction is the direction in which the world volume of the D3 brane extends, and the 6th direction, for some reason, is the one in which the D1 brane extends. And then the standard picture is, if you have these D1 branes ending on D3 brane, then you have a monopole appearing. This is just the endpoint, this naive picture. And if we want to describe this configuration from the perspective of the D1 branes, what we need is, as usual, adjoint scalars, which describe the fluctuations of the D1 branes transverse to the along the directions of the D3 brane. So we have 3 of these adjoint scalars taking value in UK, where k is the number of D1 branes. And since this is a BPS configuration, the dynamics is described by the BPS subsector of maximally supersymmetric Yang-Mills theory. And this is just in one dimension, this is just a NAM equation. I chose here a special gauge, so I gauged away the gauge potential along the S direction. This is why this is in this form. And I'll always use S for the X6 direction because this is the common thing to do in the literature on NAM transforms. Okay, so first of all, note that this is of course SO3 invariant because I can rotate everything in the 1, 2, 3 direction around the location of the monopole and nothing will change. And we can now try to find a simple solution. Simplest ansatz is probably a product ansatz. So we have our xi factorized in a radial dependence or an S-dependent part and a constant matrix part. And what you find then is that you get the radial part should go like 1 over S, and this constant matrix part forms the representation of SU2. And this is really old stuff going back to these people, and then Myers also. Yeah, okay, so here above is our solution again, and we have the 1 over S dependence, we have the SU2. And so we see from this 1 over S dependence of that our first picture was actually too naive, that we had a flat D3 brane and a stack of D1 branes ending on it. Of course, this cannot happen, that you have such a not smooth transition. So what actually happens, the D1 branes of course pulls on the D3 brane and pulls it into this shape here, right? So you get this funnel appearing. But how can this be that a D3 brane, which we have here in the far at infinity, turns into a D1 brane, right? Because the world volume directions don't match. So what actually happens is, if you look at these equations closer, then an additional constraint which you should impose at least form an irreducible representation of SU2. And for that reason, they are coordinates on a fuzzy 2 sphere. So what happens actually is that at every point of the world volume of the D1 brane, every single point polarizes into a fuzzy 2 sphere. So it gains spontaneously 2 spatial dimensions. And this is the way in which the D3 brane with 3 spatial directions and 1 temporal direction can turn smoothly into D1 brane, which has 2 additional non-commutative directions, right? So the D1 volume polarized, we have an increase of dimensions from 2D to 4D, and this is sometimes called the Myers effect, and this is well known beginnings of the 2000s. Okay, so how do you lift all of this up to M theory? It's very trivial. This is our configuration in type 2b. We just titularize along the x5 directions, get this configuration in type 2a, and then we interpret the 4 direction as the M theory direction, and we arrive at this configuration here. So how do we describe this? Well, now we have the M2, M5 branes, and they share a spatial direction, this 5 direction. I mean, here I drew a squiggly line, but actually here in this configuration, of course, it would just be a straight line. And so the endpoint is no longer, the boundary of the M2 brane is no longer a point, but it's a one-dimensional object, a string. This is why this is called a string. And furthermore, as you probably know, and we come to this later, in the M5 brane world volume, there's a self-dual 3 form, and this is why this is called a self-dual string. And how do we describe this now? Well, you can have a simple guess. You have the SO3 invariant NAM equation that describes the D-brane configuration. Now you see that this whole configuration is SO4 invariant. So we have to get something that's SO4 invariant. Well, let's replace the epsilon with 3 indices with the Levi-Civita symbol with 4 indices. And then we get this equation here, right? Never mind that there's now a strange 3 bracket appearing. Let's just assume that we can write down this equation. And let's see what kind of solutions we can find. Well, again, using a simple product ansatz, we get this relation here. So radial ansatz and a constant algebra part, whatever these objects actually are. And if you assume that the bracket is linear, then you just get that R of S goes like 1 over square root of S, and you get this relation in here. Okay? So this idea of extending the NAM equation to something SO4 invariant with roughly these arguments is due to Basu and Harvey from 2004. Okay, let's look at this equation again. So what we have again is that the M2 brane doesn't end discontinuously, of course, on the M5 brane, but we have a smooth transition between M2 and M5 branes. There's again this fuzzy funnel opening up, right? But now the points on the world sheet of the M2 brane should polarize into a fuzzy 3 sphere, so that we get a dimensional increase from 3 dimensions of the world volume of the M2 brane to the 6 dimensions, which are the world volume of the M5 brane. And now there are 2 obvious questions. First of all, what is this strange triple bracket which we have here in the game? And second is, what is a quantized 3 sphere? Okay, so here again I wrote for you the Basu-Harvey equation. I inserted back the gauge potential along the s direction, and then you get this equation. So what you want to demand of this algebra, of this construction where the x's live, is actually that it should be a vector space. You want to add things. Things should be linear, so you want a linear space, a vector space. Moreover, this bracket should be trilinear and totally antisymmetric. Everything that's not antisymmetric would be killed anyway. And then another property that you can demand, just analogously to Lie algebras, is that you don't have this 3 Jacobi identity, which is also called the fundamental identity. And this just tells you that if you act with a 2-element 3 bracket on an inner 3 bracket, and it's the same as acting on the first element, the second element, and the third element. And these objects have been around for quite a while. They've been studied by Filippov exactly in this form, and he also generalized them to arbitrary n Lie algebras. It's clear then you just have more slots, and the Jacobi identity becomes longer. That's the only difference. Now something very nice happens because of the Jacobi identity. We have a Lie algebra of inner derivations, and this is the following. We can define a map from the antisymmetric tensor product of this 3 Lie algebra with itself to these inner derivations, which just act by this 3 bracket, and the linear span of these operators is just what we call the associated Lie algebra, or the algebra of inner derivations. And it's quite nice that we have this around, because this is exactly what we need to define this action of this gauge potential. So we immediately have a gauge symmetry also on our action, and then you can verify this very trivial computation that the commutator of 2 such actions closes into another inner derivation, and this is due to this fundamental identity. Okay, so let's look at a few simple examples. Well, most familiar examples in physics probably the Heisenberg algebra and the Lie algebra SU2. They are analogous algebras, 3 Lie algebras. So the analogous one is the 3 Lie algebra. So you have a 3-dimensional space, 3 generators, and you just impose this relation, and one is supposed to be central in this sense. And the analog of SU2, which is here, is A4, which just takes this form. And you see that here this is actually SO4, the tensor of SO4 there, so you expect some SO4 invariance. And this is why this is a very nice algebra to use, as we see later on. Now, if you assume that the Basu-Harvey equation, the equation that I showed you in the last transparency, is the BPS equation of M2-brane model, then from you have automatically your supersymmetry transformations for the model, essentially up to a little bit of educated guessing, and then you realize you can't quite close the supersymmetry algebra. You also need a topological degree of freedom in the gauge potential, and if you do this, then you arrive at the Beger-Lambert-Gustafsson model. Now you can endow this 3 Lie algebra with a metric which is compatible with the action of these gauge transformations, which are encoded in the Lie algebra of inner derivations. But if you demand that this is positive definite, then you find out quite quickly that the only examples of 3 Lie algebras are actually A4. So this 3 Lie algebra here, and its direct sums, they're all allowed. But there's a problem that A4 presumably is somehow related to 2 M2-branes, and of course we want to get more, we want to get something more general. So what can we do? Essentially there are 2 ways out of this problem. One is either to switch to Lorentzian 3 Lie algebra, so to neglect that to do with a 3 Lie algebra which doesn't have a positive definite metric. And the other one is to sacrifice manifest supersymmetry, and there were 2 ways of doing that. And so this is a not quite as popular way, which is what we called real 3 Lie algebras. And what we did is just we looked at the Beger-Lambert model in superfield formulation, and we said, okay, we want to preserve at least 2 supersymmetries there, and then you get that the bracket should satisfy the same axioms as for 3 Lie algebras. However, it needs to be antisymmetric only in the first 2 slots. And the other approach is to preserve n equals 6 supersymmetry, and then you get actually a complex vector space as your 3 Lie algebra, and you get a bracket which satisfies these rules here. This was done by Beger and Lambert, and before them actually already the ABGM model was written down, which uses implicitly such a structure, and this uses this 3 bracket, and these are just matrices of UN. Okay, so, and then you can put this all together in a rather nice way. I mean, there's a so-called Faulkner construction of these 3 Lie algebras, and there's a paper by Figueroa Farrell et al., which put this into context, essentially. You can construct them from certain groups and normal orthogonal representations of them. So I should say in the very beginning that all our constructions, all the constructions that are shown in the following will generalize from 3 Lie algebras to these two types of 3 algebras. So you can do it in a very general way. Okay, so let's come back to our monopoles and self-dual strings. So the monopoles are given by this configuration. It's a BPS configuration. Now, if we switch the perspective from the D1 to the D3 brane, we just get the Bogomolny monopole equation, right? I mean, the world volume theory of the D3 brane is just maximally supersymmetric Yang-Mills theory. We restrict to the BPS subsector static configurations, we get the Bogomolny monopole equation, right? Because of the Bianchi identity, this immediately implies that phi is a harmonic function in 3 dimensions. And if you have a single D3, then we just get the Dirac monopole. And for harmonic functions, we get a Higgs field which goes roughly like 1 over r, up to scales and up to constant terms and so on. And this, of course, matches now exactly with this R of S solution that we found from the NAM equation, right? Because this direction, which is the phi direction, is parameterized from the NAM perspective by the S coordinate. And so we should identify phi with S. And then this equation, of course, is compatible with this. You get a matching profile exactly as you would hope for. Now, in the M theory picture, we can switch perspective from the M2 to the M5 brane. And that means that you get the self-dual string equations, which are given here. You can derive them in various ways. I don't want to go into details. But again, you see from H, which is the curvature of a two-form potential, that the Bianchi identity again tells you that phi is a harmonic function. Unfortunately, we don't know the theory here for in the non-abelian case, but only for a single M5 brane we can write down this equation. But still, what we get is that we have a Higgs field, which goes like 1 over r squared. And doing again the identification that the S direction is the direction of the phi field, we can compare to the potential, to the profile that we found before, which is R of S. This goes like 1 over square root of S, and of course this matches again. So you get matching profile no matter how you look at this configuration. Okay, now I need a little bit of mathematics I need to remind you of, namely the description of Dirac monopoles as principal U1 bundles, because I can then very easily lift this up to description of self-dual strings. So first of all, recall that you have a manifold, you have a cover UII, and we take a principal U1 bundle over this manifold, and we can describe this because it's an abelian bundle by a globally defined curvature two-form, and using Poincaré lemma, of course, then you get on the patches, can write it as d of a potential, and using the Poincaré lemma on intersections of patches, you get that you have a transition function Gij, which is then related in this way. So this is the usual way of using Poincaré lemma to trade de Rham cohomology degrees with check cohomology degrees, and the description of a principal U1 bundle. Now, if we want to describe a monopole in R3, then you remember that the phi field had a singularity, the Higgs field had a singularity at the position of a monopole. So we don't want really to go to R3, but we describe it rather in terms of S2. We can foliate R3 by S2 and take out the origin, for example, or just look at one S2 in this foliation. And then if you have a principal bundle over S2, of course we have patches U plus U minus. Intersection can be contracted to the equator of the sphere, and the transition function is then of this form. And then we can use the standard calculation to compute the first Chern number as an integral over the curvature, and use then Stokes lemma and so on to find that the monopole charge is indeed k, and it's quantized, it's an integer. Okay, so this you probably all know. How do we lift this up to self-dual strings? Well, here you need something which is called an abelian gerbe, or local. We just work with local abelian gerbes. It's very simple, actually. Sounds more scary than it actually is. So you start from a manifold again with a cover, and instead of starting from a two-form field strength, we start from a globally defined three-form field strength. Then the Poincaré lemma tells us, okay, on patches we have two-form potentials. On intersections of patches we have actually one-forms. And on triple intersections we have something, if we take the logarithm of this, we get our old transition function back, which is related to some crude prescription there, but I don't want to go into details here. So you have a similar structure. You start from just from 1 degree in the Rham cohomology, which is higher. If you consider S3, then we can again cover S3 by patches containing a north pole and a south pole, right? And the intersection can then be contracted to the equator, and the equator is then, it can be contracted to an S2. So we learn that because we have one form over intersections, so a gerb can be identified up to certain compatibility conditions with a line bundle over intersections. The intersections are can be contracted to S2. So a gerb over S3 is nothing, well, topologically it should have the same characterization as a line bundle over S2. And this is precisely reflected in the fact that the second cohomology of S2 with coefficients in Z is isomorphic to the one of H3 of S3 with coefficient in Z, and this is Z. So the monopole number should be reflected here. We should expect also a topological invariant, which would be the charge of the topological string. And again, you can go through the calculations here. You can integrate H over S3 to compute the analog of the first Chern number, so it's called here the Dixit-Medoradi class, and you find again it's quantized, and we call this the charge of the self-dual string. So the structure from the monopole lifts up to the case of the self-dual string, and you get exactly the same structures, just you start from 3-form field strength instead of the 2-form field strength. Okay, but now a gerb is still a little bit scary. We don't really want to work with 3-form field strengths, and because we don't know how to make it non-abelian and so on, and there are various other issues. But there's a trick to avoid doing this, and this trick is called transgression. The way this works is as follows. You have here your manifold, and you have your loop space of your manifold. And now you can establish a so-called double fibration by just putting here the loop space of the manifold cross S1. And the fibration is given as follows. So first here, this is a simple one. We just have the projection, right? Just drop the S1. The other one is more complicated. Well, it's not more complicated. You have an angle, and you have a loop, and you just evaluate the loop at this angle, and you fall down to your manifold. Okay? Then if you think a little bit about the structure, you can identify actually the tangent space of the loop space of your manifold with the loop space of the tangent space of your manifold, modulo some issues concerning reparameterization invariance. But if you're careful, then you can do this. And then you see that if you have a loop, so an X in your loop space, you have a very natural element in the tangent space of your loop space of your manifold, which is just a tangent to your loop at each point tau, right? This defines an element of this space. And we can use the existence of this element now to introduce the transgression map, which is a map from a k+1 form on M to a k form on the loop space of M. And the way this works is as follows. Well, we want a form, so we want to be able to contract it with vectors and get out a number. So that identification with the tangent of the loop and the loop on the tangent. Yeah.
Surely that's only local. Surely that won't hold globally.
Well, the way you can think of it is just you look at a vector, right? And a vector has components vi, tau, and
it is true globally.
It's globally, yeah.
It's true globally?
Yeah, I mean, you can just look at the components. Right?
The components are local, but as vector bundles, it's true.
Yeah, sure.
It's not true for the cotangent bundle, actually, but it's true for the tangent bundle.
Okay, it's not obvious though, right? That it would be.
Well,
okay,
True is obvious.
I can show if you look at what a vector actually is, it's fairly obvious. Okay.
I'm
So
just
doing some
concerned about this.
Okay. So anyway, let's try to continue.
So if I don't ask questions, it doesn't change colour.
Questions thinking.
Good trick.
Yeah, the issue here is only you have to worry about reparameterization invariance. This is the only thing which matters.
It's just I could imagine twisting the tangent bundle globally and then taking a loop space over the twisted tangent bundle seems to be quite involved as opposed to just taking only loop.
Well, we can discuss it later on.
It's true.
It's true, yeah. I mean, yeah. For the cotangent, but yeah, let's discuss it later. So, okay, so transgression map, let's put it together. So a vector field has these components, any vector v nu, and it's contracted with this differential variational derivative along the loop. This is an element, so we always have as a component of our vector v nu of tau. And if we now want the transgression of omega, we contract it with k of these vectors, right? I shouldn't have put tau here, sorry. Then what you do is you just take our original form at the point x of tau, you plug in, you contract it with these elements, v mu of tau at the point tau, right? The mu indices will contract the indices of the omegas, and the last slot is just filled with this natural tangent vector that we have on loop space. So in this way, you just integrate over this, you get a number. This is reparameterization invariant because the x's are reparameterization invariant, these objects are reparameterization invariant, and this one changes inversely to the measure on the loop. So this is all really well defined. And what we learned from this is because we can map a 3 form on the manifold to 2 form on the loop space of the manifold, is that an abelian local gerb over M, the thing that we use to describe gerbs and self-closed strings, is a principal U1 bundle over loop space. Okay, so then we are back in the ordinary description of gauge theory, if you want. Okay, here's again the transgression map, now written in components. Right, so you see that these indices here are really contracted, and these will be our generalized 1 forms on loop space, and the last ones then contracted with a tangent vector to the loop here. The properties are, well, a few remarks. First of all, you should note that the integral doesn't only go over the coefficients. Some people did this in papers and then things don't quite work out, but you really need to take into account that you're integrating over these forms, and these forms are Tor dependent. Second, T is representation invariant. I already stated that. The third property, which is very nice, particularly when we want to do gauge theory, is that the transgression is a chain map, and this means that if you have an H which is dB, and you transgress the H, then it's the total derivative on loop space, the exterior derivative on loop space, times the transgression of your potential. And moreover, because of the Bianchi identity here, you have the Bianchi identity on loop space. And yeah, but this just means chain map, right? Closed forms are mapped to closed forms, and exact forms are mapped to exact forms. A property which I'll briefly refer to later on, if you have a function on your manifold, and you take the exterior derivative of that, you transgress it, you get 0. It's just a property. Then I should stress that the transgression is not surjective. Of course, there are many, many more forms on loop space than you can arrive at using the transgression map. So the inverse, which is sometimes called a regression, is only defined on the image of the transgression map. And furthermore, because T is not surjective, there are many more line bundles over loop space than gerbs on M. Of course, this statement is only true up to equivalences and gauge equivalence and isomorphisms and so on. But here, suppose that you use the usual gauge equivalence that we would use in physics, then you will find that you get line bundles which don't correspond to gerbs on M. Okay, so a side remark of how we can use that is a quick going back to this question of how you quantize S3. And then you can remember that in geometric quantization we have the following prescription, and this gives us, for example, the fuzzy tooth here. You start from a special symplectic manifold. I mean, special here means that it's essentially a projective algebraic variety, so you can embed it in CPN, but that's not that important. Then from this 2 form, from the symplectic 2 form, you get a line bundle, just as I showed you before, and you also get then the curvature. This will be the this is the curvature of this line bundle, and you can write on a connection and the metric in the fibers which is compatible with this. And once you have this line bundle, this special guaranteed you that it has interesting global holomorphic sections, and this is what you identify with your Hilbert space. And this is how you can, for example, obtain the fuzzy sphere, and then you can define various quantization maps which satisfy the correspondence principle up to first order in H bar. Okay, this is how you do it on the fuzzy 2 sphere, and there everything is clear. However, on 2-plectic manifolds, the question is now, what do we do here? Well, we have a manifold and we have a 3 form now. So the 3 form defined gerbs. So we want some holomorphic sections of a gerb. That's not quite clear what this should be, although some mathematicians probably know how to define that properly. Then we would have a quantization map which maps this 3 Lie algebra structure to some.
Symplectic means the same as 1-plectic, is it?
It's symplectic, 1-plectic, yeah. It's actually shifted over 1 degree.
One in Greek or something.
No, it's a categorification essentially of the symplectic structure. And 1-plectic is, yeah, it's like a vector bundle is a 0 gerb.
What does the sim mean in symplectic? In fact, what does the plectic mean in symplectic?
Somebody else might be more qualified to answer this properly.
Any Greek scholars?
Any Greeks in the audience?
Yeah.
Greeks.
Simis?
Sim is plus and plectic is braided. So
Right. Okay.
What is it again?
it's braided.
And sim was
Plus. Sim is plus.
Oh, I see. That's great.
Okay, so we have a 2 braided manifold here. But so anyway, we have this 3 form which would tell us, okay, we should somehow take holomorphic sections of a gerb. We're not sure how to do that. Then a quantization map should somehow go into 3 bracket. Well, it's true that if you have a volume form like we have on S3, that you can define an analog of the Poisson bracket, which is called Nambu-Poisson. You'll hear more about this later. But yeah, we're not quite sure about this, right? So what one can do is one can use this 3 form to define a bracket on 1 forms, or so-called Hamiltonian 1 forms. On S3, turns out that all 1 forms are Hamiltonian. And what you do is you just mimic the definition of the usual Poisson bracket. That means you define for each 1 form, you define a Hamiltonian vector field in the usual way. There's an omega, there's a 3 form missing, sorry. And then you define this bracket just by contracting the corresponding Hamiltonian vector field with a 3 form, giving you a 1 form. And this is the so-called semi-bracket that Weiss et al. Introduced. This bracket is antisymmetric, but it doesn't satisfy the Jacobi identity. It's violated by a term which is an exact 1 form. And then also the quantization of 1 forms is not really nice. So there are lots of issues here which we need to clarify, which would have to be clarified to approach a quantization of S3. However, we have now our fancy transgression map, and the solution is just we define a symplectic 2 form on loop space by transgressing the 3 form, right? Then we immediately have this compatibility condition with this bracket on 1 forms. So this was already the right direction, but not quite. Once you transgress it, it actually becomes a full Poisson bracket. Everything is satisfied, it's antisymmetric, Jacobi identity holds. And what this tells us that instead of quantizing 1 forms, one should really quantize functions on loop space. And then we can just use this procedure up to some difficulties which are related to the fact that loop space, of course, is an infinite dimensional manifold. Right? Can give you a very quick flavor of how this goes. So we.
Sorry, how do you use the fact that, did you say it's not subjective, so that you've got things? I mean, so if you say you're going to quantize them on loop space, but the point is there are more things on loop space than there are transgressed from.
Right. I mean, if you look at this,
it's a lot of redundancy.
Yeah, in a sense. I mean, you see, in this case of the symplectic manifold, you use the 2 form to define a line bundle, right? And of course, you don't take any line bundle. There are very special 2 forms, and you have to choose special symplectic manifolds where these ample or positive line bundles really exist, right? So it's already here you're picking very special line bundles. But the only thing that you want here really is you just want a sequence of line bundles that allows you to approximate the function space on loop space better and better. And for example,
no, you're missing my point. I mean, so there's 2 things. You're saying you want to quantize loop space, which is fine, and then you're pointing out how you might do that.
Yeah.
But as you say, the original problem is that you want to quantize gerbs.
Yes.
And then, but there's not a one-to-one map. So then the point is, just because there's many things in loop space that are not from gerbs, if I quantize the loop space, it seems like I've got a huge whole bunch of stuff that's not.
I mean, in the quantization problem, the only thing I need is a 1 bundle over the space I want to quantize, right? And this gives me a way of 1 bundle.
No. You can solve the quantization problem over the space. That's not the point. The point is, originally you had a problem that was to do with gerbs.
Sure.
And then when you go and you go into the space of loop space, but loop space is bigger.
Sure.
So then, yes, you can quantize that loop space. But what's that got to do with the original problem?
You've got to find a way to take a restriction to the image of the transgression.
That's right.
And then there is a known inverse.
Well, and also you might
quantizing.
Well, you might argue that
I'm worried that then because of the redundancy.
Yeah, of course there's redundancy, but you might argue that the gerb picture is actually not complete. You might argue that the gerb picture is just a linearization of what you actually want. And this is exactly what how I like to think about gerbs. Gerbs is just a linearization. It's a first order approximation, if you want, so to the loop space picture, which is the full picture actually, right? And
I could buy that.
And this is exactly so. This is all just the motivation why you should consider loop space and why you get a nice.
Quantization is never unique in anything.
Exactly.
It's
right.
the other way that you get. So you start with the quantization and go backwards.
But I'm more thinking.
So you shouldn't worry too much about that.
Yeah, I'm just giving you a prescription how to quantize S3 by saying it's one prescription. I'm not saying that it's the best.
I'm not worried about the quantization.
Yeah.
I'm worried about the fact that it looks like you've
enlarged the
added
space
in a lot
unnecessarily.
more. Yeah,
Okay.
you've added in a lot more.
Well,
classically, I can see how you project down, but then I'm worried when you quantize. It's like quantizing a gauge theory, right?
Right. But I mean, we don't know how to quantize gerbs, right? I would claim that you don't know how to do this prescription. Mathematicians claim they can do the holomorphic sections, but nobody knows how to do the polarization.
No, I mean, if you go to Henno and Tietelbaum, Henno's book rather. Go to the Henno book. I'm sure he does 2 forms in canonical quantization.
Yeah, in canonical, but not in this language.
Yeah, he's abelian here.
No, well, you can do flat space, but you can't do S3, you can't do compact spaces. First of all, that. Then I spoke to many mathematicians about this. Nobody knows how to do polarization for jerks. Well, you can do certain polarization for jerks, but they are not the ones that you really want there. So there are, I thought about this quite a lot, actually. There are quite a few problems which are still open there. I can discuss that afterwards with you. It will take a little bit further. But, okay, but yeah, of course, I mean, we go to larger space and we trade the difficulties with the jerk for difficulties dealing with an infinite dimensional manifold. However, I mean, my point of view is that jerks are just a linearization. This is not good. It's not good to quantize one forms, right? And these brackets, they are very restrictive. They don't seem to be the real answer either. So while here I can do everything works out nicely. And you see even the result that you had in your paper here.
Well,
so
I have it, must be right.
Yeah. We're convinced you now, right? So we
my
start.
objections are immediately withdrawn.
So we start from R3. This is just an example of how this would work. So you get a two-plectic form, which is just a volume form which we use. Then you transgress that, you get a symplectic form on loop space, which just looks like this. So we just took the component, contracted the last index with a k. Right? Now these forms are actually reparameterization invariants, and you can show that they're invertible. There's a little bit of work to do. They're invertible up to reparameterization invariant. But then you see that you can define a Poisson bracket, which is given by this on loop space. And then you would want that your correspondence principle holds. And that means that the commutator of two such coordinate functions on loop space, if you want so, should be the quantization of the Poisson bracket, right? So you should have probably put operators on top of this. And then you get this result. So the commutator of two functions actually is epsilon times theta, and then you get the tangent vector to the loop, and you have to divide by this for renormalization, reparameterization invariance. And this is only in first order in theta, second order in theta. One has to compute if there's something new in your paper. There's nothing there, but there might be something there. This is all rewriting coordinates.
And we got the all order theta result in later work.
Ah, right. Okay. Thanks. Yeah, we should discuss that later. Okay, cool. Yeah. Okay. This is Kawamoto, Sadako, and Baxter Berman et al. In 2000, and we got also some quantum corrections, which hopefully come out in March actually, and more possibly should advertise. Richard's talk next week might appear there. Okay, let's return to our self-rule strings, and let's look at the transgressed equation for them. So our self-rule string equation is this equation here, right? So we want to transgress that. What we get is an equation, because this was an equation on 3 form, we get an equation on 2 form on the loop space of R4, and it looks like this. And then we transgress the right-hand side, which gives you this expression, right? Or we can write it in components, and then it just looks like this. So we have mu sigma, mu rho, this 2 form on loop space, get a delta function here and the transgression, and then we get here this object. But the problem is that this object is really not an object on loop space, because this is still the derivative on ordinary space-time to phi, so we want to correct for this. Furthermore, you see this has a delta function in it, so this was together with this thing. It originates from a transgression, so it's what's called an ultra-local expression, and we want to have this more general. So the actual equation that you need to generalize this is the following that's given here. So it essentially looks similar. We just took out the delta and put in here an additional derivative at position tau. Furthermore, we immediately made this non-abelian, because there's no problem in loop space with it. So this is a nabla actually, it's a non-abelian self-rule string equation, and then you get these additional terms here, which correct for the fact that we are that this was just a function of ordinary space. However, here we want to be on loop space. And our goal is now to construct solutions to this equation, and we claim that this is a description of self-rule strings on loop space. Okay, now first to present the algorithm, I should show you how this is done for monopoles. And this is the so-called ADHMN construction that I mentioned already in the beginning. It's a special Nahm transform. So Nahm transform maps instantons on T4 to instantons on the dual 4 torus. And roughly here, without insulting too many mathematicians, think of a 4 torus which has 3 radii 0 and 1 radius infinity. And this 1 radius infinity is roughly the D1 world volume. And you dualize this to another torus which has 3 radii infinity, 1 radius 0, and this is the D3 world volume. If you like this picture, think of it this way. If you don't like it, forget about it, right? Okay, so what you do is you introduce a so-called Dirac operator, which is a Dirac operator acting on the one-dimensional world volume of the D1 brane, and then you give it also a so-called twist. If you know this Nahm transform, and this twist originates from the twist by the Poincaré line bundle in this transition, and this is the Dirac operator that you have. You also consider the adjoint, And you find that this Dirac operator is positive and commutes with all the sigma matrices, so it's easily invertible, if the xi, which enter the definition of the Dirac operator here, satisfy the NAM equation. Okay, so this is how you connect to the NAM equation. The solution to the NAM equation, you have a Dirac operator which has nice properties. And then you can show, if you take the zero modes of this Dirac operator, you normalize them properly, and then you get a gauge potential in this way, and the Higgs field in this way, and these are forming these solutions to the Bogomolny monopole equations. So again, you have a solution to the NAM equation, construct your Dirac operator, get the normalized zero modes, and calculate these formulas. You get a solution to the Bogomolny monopole equation. And this is the construction that I'd like to mimic in the following. So have a quick look at the trivial examples. So if you have a charge 1 monopole, the NAM equation becomes abelian. So we can just put these to 0. And indeed, if you look at the zero modes, you get the monopole solution for the Dirac monopole. You have a funny normalization. So my Higgs field always goes with k over 2, where k is the charge. So this would be charge 1. If you have the NAM charge 2, then the NAM equation is non-trivial. The xi take values in SU2, and you have then this ansatz here, exactly the product ansatz that we had before, right, which goes like 1 over s times the representation of SU2, and the resulting solution then is really Higgs field with charge 2, so twice the charge compared to this one. And you can also compute the gauge potential, but it looks a little bit messy, so I didn't write it down. Okay, so you can compute easy solutions, it's just what I want to show you here. Okay, now let's lift the Dirac operator to have this construction really work on M-theory. Here's our Dirac operator in type 2b. Now we go to type 2a. Type 2b was a chiral theory. This is not chiral, so we expect that the sigma I actually replaced somehow by the gamma matrices, right? The chiral spinner, non-chiral spinner, the Dirac spinners really. And then you can choose any embedding of SU2 into SO4 with these matrices, and one solution would be this Dirac operator, and this had been used in the literature already before to describe D2, D4 branes, and this is all fine. And now the lift to M-theory is no longer that difficult, because if you interpret the 4 direction as the M-theory direction, the SO3 invariance becomes SO4 invariance, and of course the gamma 4i should be replaced by gamma mu nu. And the xi, what can we replace those by? Well, fortunately we have this algebra of inner derivations, which allows us to pair up 2 elements of the 3 Lie algebra and contract them into that. So this seems already quite good for the unquestioned Dirac operator. And the big question is now, how do we do the twist? And then fortunately loop space comes to the rescue, because on loop space we can take the coordinate and the tangent to the loop and integrate over both of them and contract them with the gamma matrices. And then we really get an object which is well defined in loop space. And furthermore, we have something to contract the gamma matrices with 2 indices without problems. Ordinary space, we couldn't do that, right? You can't construct anything antisymmetric out of your coordinates in an easy fashion. So this is very nice that we have this on loop space. Okay, so the question is that really what we want? So
How about the relative factor?
Sorry?
How about the relative factor, the twist in term with the rest? Why did you write -I? You just motivated the last term.
Well, this is some reality condition that I had in the paper. There's no deeper reason for this.
Is there what?
There's no deeper reason for this. You can also drop the I. I probably just copy and pasted this formula without it.
If I put the 7 in front of the I, will this?
No, you need a 1 over R, exactly. I'll explain this later, how you reduce this one to the Dirac operator. Okay, so now this was an educated guess. Now we have to see if this really satisfies all our properties. The key property was the Laplace operator constructed out of the Dirac operators had nice properties if the xi satisfied the NAM equation. Here we get the following. The Laplace operator constructed out of this Dirac operators has nice properties if the x mu satisfies the Basu-Harve equation. Inversely, this doesn't hold, but this is just a technicality which was clear because this map to inner derivations is not injective. So this was clear that you expected. However, if you have a solution to the Basu-Harve equation, we get a Dirac operator with nice properties. Then this is again my self-proof string equation. And now the guess is, of course, well, we take the 0 modes for this Dirac operator, write down these formulas, and get a gauge potential on loop space and Higgs field on loop space. And if you plug this in, then you find that these fields of indeed this loop space self-proof string equation, well, the transgressed form of the self-proof string equation, with all the non-abelian parts in place and all these correction terms in place. So this works, not a problem. And the proof, just to give you a flavor, it's really not difficult, right? You just calculate this thing. This is a short calculation, and everything works out and everything is fine. Okay, so come to the reduction, how to do that, right? So
what's that funny symbol above the equal sign?
Right. So this is equal. This is a shorthand notation because you need to antisymmetrize these things, right? I copied that from the paper. This is antisymmetric, of course, in mu sigma nu tau, but here this formula is not necessarily. So this is always equal up to antisymmetric sign. This is just a shorthand.
Interesting.
I didn't expect anybody to actually read this formula. Just wanted to show that it was a short calculation, right? That it's not too
I
long.
like to know how to do that in latex, so I can.
Oh,
That's
it's background, but yeah.
Yeah.
Oh, sorry.
Yeah?
Is this all about classical solution to the?
Yeah, this is classical.
I'm a little bit confused because I thought you were talking about loop space, etc. Because you want to quantize the job, etc. So I thought quantization.
Well, I try to give two motivations for loop space, right? One motivation is that I don't know how to quantize S3, right? I mean, I showed you that in the D-brane picture we have a quantization of S2 appearing, and in the M-brane picture we expect a quantization of S3 appearing. We know how to quantize S2, of course, and we don't know how to quantize S3. So loop space, however, gives us some idea of how to quantize S3. So this is one motivation for loop space, even though David doesn't want this. Yeah.
In a minute.
Okay. And what I'm doing here, however, is I'm using loop space to lift this classical integrability which you have in the ADHMN construction, right, to M-branes. And here it helped as well. So loop space helps in various cases, and you see a third case, if time permits, where it helps as well.
Just to comment on that quantizing S3, didn't Sanjay Ramgoolam do the quantization?
Yes, but he did it in a different way. And what he did,
Different way.
different meaning he still had associated, well, he still had matrix expressions, right? Of course, as you would have, and from the matrix expressions he constructed an algebra of functions, as you would, and representation of SO4. He mimicked essentially the naive way of quantizing S2, right? And then what you find is that you have way more representations than you have actually spherical harmonics on S3.
Yes,
so you can project down, you get something non-associative. But the question is whether you believe that, because these quantizations, they don't form solutions of the. I mean, it's all your work, right? I mean, you did this. They don't form solution of the Basel-Harp equation, right? Do you believe that this is really the right way of quantizing S3? We can discuss this later. We're running out of time otherwise.
Let's discuss it later.
Yeah, exactly. I guess that's better. But yeah, I mean.
But I was just curious. Okay, but the statement I wanted to hear is this is a different quantization.
It is a different quantization
of that one,
yeah, yes.
and the other one has the problem that it's non-associative.
Yes, exactly. Of course, we are quantizing functions on the loop space of S3, while he's quantizing functions on S3, so it's obviously different. Right? Okay. So what we are doing here, well, now let's reduce this construction that we had to the ADHM construction to show that everything works fine. And how we do that is just a prescription that you use to reduce the Becker-Lambert model to Superyang-Mills theory, as Mukian Papageorgiakis described. So what you do is you take one of your scalars and you give it an expectation value, you Higgs it, and then of course, as we would expect in the loop space picture, we have an additional prescription, which is just if you reduce from M theory to string theory, you'd expect that your loops go around the M theory direction. So you want to loop in the 4 direction, which we identified as the M theory direction. If you do, oops. That was your question again.
Thinking about
Stop thinking about the quantization. Right? And so if you loop along the 4 direction, then you see, because, well, we have the loop really only looping in this direction. So in the antisymmetric combination here, this has to be 4 and this can only be 1, 2, 3, right? Then you integrate over this gives you just the length of the loop. Then with the proper normalization, you get a nice factor here. This one, if you Higgs it in the strong coupling expansion, it reduces the associated Lie algebra of A4, it reduces it to SU2 actually, and then you just get the ordinary Dirac operator in type 2a. Of course, we have gamma matrices floating around. So this is really the reduction from M theory to type 2a. Everything works as expected. In the Basel-Harp equation, you have the same. The Higgsing directly gives you what you want, the NAM equation on the nose in the strong coupling expansion, of course, and in the transgressed form of the self-loop string equation, I wrote down the short form. Then if this is in the 4 direction, of course, this then reduces to the ordinary Bogomolny monopole equation. So the whole reduction works exactly as you would expect it. Okay, the third test would then be to, or the second test would be to construct solutions, right? So charge 1, remember for monopoles we could choose trivial NAM data. You do the same here, you introduce some auxiliary coordinates, and then you can find the zero modes, you can construct the solution and a gauge potential on Higgs fields on loop space. It doesn't look too bad. It's really a solution, you can plug this in, calculate it, and even the charge is right? You remember my normalization was always 1/2, so this is a charge 1 solution, just as we expected. Charge 2 we can do really analogously. There we use NAM data, which now lives in the 3 algebra, A4, and you just plug it in, calculate the zero modes, and you find a solution which goes like 1/r², and indeed it has twice the charge of the case k equals 1. Now, of course, we want to go to arbitrary charge, and there we have the problem that the Becker-Lambert model only comes as long as you want to deal with positive definite 3 algebras, you only can have A4, but this only describes maximum 2 M2-branes. So we have to switch from the Becker-Lambert model to the ABGM model. So for that, recall that switching from the BLG to the ABGM model means that you drop manifest n equals 8 supersymmetry, you restrict yourself to n equals 6. This is reflected that your flavor symmetry that you see on manifest part of the flavor symmetry reduces from SO8 to SU4. Right? So SU4 is SO6, so you get 6 n equals 6 supersymmetry left over. Here this amounts to the reduction SO4 down to SU2. And then you can write down the Basu-Harvey equation for the ABGM model, just the BPS equation of this thing, and reduce it to 1 dimension. And you get this expression here, where you get these complex matrices. So our 4 real values are now encoded in 2 complex ones, and we have only SU2 manifest because of that. If you look at the irreducible reductions, if you look at the irreducible solutions of this model, then you find that one of the fields has to be real. That means of the 4 components that you would expect here, only 3 are actually turned on. So this is a big drawback that's exactly related to all kinds of symmetry problems, that the ABGM model without any corrections should be regarded as type 2A and all these things, right? Without monopole operators and so on that we heard about this morning. So this is somehow to be expected. It's not quite as nice. However, we can just apply our formalism and see where we get with it. And indeed, you can construct Dirac operator. You can lift our whole construction to this case, 0 modes, etc., and you find that you really get a Higgs field which has k times the charge of the previously found ones. So indeed, our construction extends to the ABGM model, to the Saemann 3-Lie algebras, and you can also extend it to the real 3-Lie algebras, but that's physically not that interesting. Okay, so let me give a few remarks. First, I hope to convince you that the lift of the Dirac operator was natural considering the corresponding brane configuration. It's very helpful and natural to go to loop space to describe these. Of course, you can make it trivially non-abelian, right, as we saw. The construction nicely involves the Basu-Harvey equation exactly in the way that you would expect it. It reduces naturally to the AHM construction. It produces, of course, transverse left-field string solutions. It's the most important thing. You can extend it to real Hermitian 3-Lie algebras, as I showed you. And something that's very interesting in this construction is that the gauge group that you get on loop space is always of the form G cross G in our solutions. And this appeared quite a lot in recent proposals of M5 brane models, for example, this one here. And it fits exactly with the expectations from the twistor space picture, where, well, having a twistor space to construct self-field strings, you would expect that there's an underlying ADHMN construction to construct this, and this is exactly what we obtained. Okay, in the last 5 minutes, let me show you another case where loop space appears, I would say, rather naturally. And this is a set of equations that were proposed by Lambert and Kostis Papagakis in 2010. And so what they did is essentially, let's look at the tensor multiplier, let's propose some supersymmetry transformation for this, and let's close the algebra and see how well we can do. And let's use as an additional ingredient the 3 bracket, right? And what they found is then this set of equations. What you notice is that first of all, there's the usual field that you would expect for an M5 brane for the 2-0 tensor multiplied in 6 dimensions. So 5 scalars, the corresponding spinors, and here's the H field, the free-form field strength. However, there are additional fields. There is a C field, which is covariantly constant and satisfies some algebraic relation. And there's an additional gauge potential, which appears in all these covariant derivatives. And we have this equation, which relates the field strength to the free-form field strength. Okay, so first of all, this equation here suggests that somehow C has to factorize, right? So we have a constant 3-Lie algebra part, and we have another part. Of course, from the loop space perspective, it's very natural to assume that the other part is just a tangent to the loop. And then we can use some kind of 3-Lie algebra transgression. That means we interpret this H field, and we transgress it, but we also contract it with C to get from a 3-Lie algebra object to an object in the inner derivations. And if you work, for example, with A4, this would just be SU2. So if you work with ABGM model, then you can get arbitrary gauge group here, essentially. And now if you look at this equation, then you see that this looks very much like a transgression map, right? If the CL lambda really factorizes in this way, the tangent to the loop, then this is contracted, and then this is nothing but the transgression map, right? So then you can, if you make this observation, this looks like a transgression map. Let's try to transgress all of these equations and see what happens. And indeed, you can do that. So you can transgress also the matter fields, because, well, you need to do that just to make sure that they live in the Lie algebra, not in the 3 Lie algebra, and so on. This is something that they tried to do something similar. They didn't quite do it in the same way. It didn't arrive at the closure of the supersymmetry algebra. However, if you do it the way I suggested, then you get these equations here, and these are very close to just super Yang-Mills theory on loop space. So if you want, to a certain extent, if you like these equations, then this could just be equations for 2-0 tensor multiplet reinterpreted on loop space. You get supersymmetry transformations, which are here, and yeah, everything works exactly as expected. Okay, a few remarks about this. First of all, we get super Yang-Mills theory on, or some theory like this on loop space from the tensor multiplet. Interestingly, the BPS equation is exactly the loop space BPS equation that we obtained, that we use in our construction, ADHMN construction on loop space. We use a reduced loop space derivative which just takes into account zero modes. This is a little bit annoying, so if one really wanted to make this rigorous, one should probably get rid of this. Technical issues like a Laplace operator on loop space is a very nasty object actually. So well, you can define something like this, but it's not straightforward. So I think this is the right direction, and more work is certainly in progress to get rid of certain limitations of this approach. Okay, let me conclude just before time. So what I did is I reformulated the self-two string equations on loop space, showed you how to generalize the ADHMN construction so that this all works. We found in November this classical integrability from the twistor picture. So this is exactly underlying this whole construction in a certain way. We get explicit constructions in many cases, and we could reformulate the non-abelian tensor multiplet as equations on loop space. And then for that, we can generalize the ADHMN construction. So future directions, of course, would be, the dream would be to find the 2-0 theory using loop space, but before this happens, it's reasonable to study the classical integrability in more detail. So, I mean, if you know classical integrability in the twistor story, there's a wealth of results on monopoles that just waits to be lifted to loop space, or to self-two strings, essentially. If you want to discuss spectral curves, which I'm currently working on, and also make this twistor picture here, which was just abelian, because it's really working with free forms, to make this non-abelian. Then you can discuss higher analogs of what's called magnetic bags. I didn't come to this because I'm running out of time. And then the loop space quantization of S3 and so on. This is what Richard might talk about next week. And then there's also a second branch of this quantization of S3 by Gerb, so that we avoid this doubling or redundancy in the degrees of freedom and two groupoids. And these are things that are currently in work, so I hope that this works out. But I try to convince you that loop space is actually a very nice thing to use in the context of M-branes. Thank you very much.
Questions? As you pointed out at the beginning, when you discussed the realizations of the three algebras, that you have the A4 and so on, but and then of course there's the Nambu bracket, which you had.
Yes, exactly.
Now, that's another direction that various people have taken. Mm-hmm. One of the problems with that is that is essentially basically comes down to the problem of quantizing this S3.
Exactly.
So I mean, in some sense, that gives you an infinite. Can be viewed as some kind of classical even sort of because you've taken a finite number of them and you've gone to some continuum limit. Okay. So in order to go backwards, you wanted to so the problem of quantizing S3 comes out that way. And various people had, there were all kinds of suggestions about that in the past. Mm-hmm. It struck me that at some point you were saying that you've been able to, you have a way of quantizing S3.
Yeah, I should point out that this idea, of course, using loop space in geometric quantization is really old. It goes back to Gawecki, and it's not my idea. So this is a standard, easy way to do that. What we are doing is really working out all the gory details and finding a nice way to getting the corrections and so on. And there's an issue of polarization, which is not.
My question was simply that why do you need to then go to ABJM? If you, because quantizing S3 was essentially the problem with that other approach.
Yes.
Where you had n=8 supersymmetry. Yeah. The reason that we had to go to ABJM, it was because we couldn't quantize S3.
No, of course, completely.
So it seems to me that if you can quantize S3, that's.
Yes, but remember that the loop space picture here, it was a little bit split, the whole discussion. The loop space picture appeared on the M5 brane side of things. The M2 brane side of things was still ordinary 3 algebra things, right? So I think that you can potentially reformulate the BLG model also in some loop space language, and then you would get rid of this quantization problem of S3 within this context. However, since we are working, I wanted to make, of course, contact with what everybody does, so Basel-Harvey equation and so on. And so we stuck to the ordinary BLG formulation. However, the BLG has problems, as you point out, there's only A4 and so on. If you reformulate this in certain ways, then I hope that one can overcome these obstacles. And this essentially, it was this dichotomy that I had loop space on M5 branes, but M2 branes are still described in the ordinary way. And if you think how the NAND transform works actually, right, you have a theory on a torus and a theory on a dual torus, right? And then you can go back and forth just because the theories are Young-Mills, they're the same essentially, right? You just dimension reduce them. If you hope to get something like this working for M2 and M5 branes, of course we need to have a theory on M5, hopefully some loop space theory, but also a theory on M2 which is on equal footing, right? We can have different theories connected in this way. This wouldn't really work. So what's also missing is a reformulation of the BLG model in this spirit at least, right? And there are interesting directions in which one can look and get a few ideas how one can do that, but it's too early to say anything reasonable about this.
Any other questions?
Okay.